Yeah, I think perfect. And then you can share your screen. Thank you.
Okay, I will share my screen. Okay. Do you see my screen? Do you hear me? Yes, yes. Okay,
yeah,
okay.
Yeah.
Okay, so well, first of all, good morning, everyone. Thank you very much to CIRCE to organizing this workshop regarding the CO2 capture, the storage, and the conditioning that, different technologies will be explaining along this morning. I think that it could be very interesting because, apart from the different technologies that maybe some of them has been demonstrated in the different demos. For example, our talk that is focused on the membranes, we don't carry out these membrane processes in this CAPTUS project, but I think that this could be very interesting for to share our expertise in this field and maybe share with all of you our expertise in this topic in order to see future synergies between us and the other partners of this CAPTUS project. First of all, as you may already know, we are part of the process group, the Chemical and Biomolecular Engineering Department at the University of Cantabria, and our main research interests are focused on the development of CO2 capture and utilization processes. And although in this CAPTUS project, as you know, we are in charge of the third demo of the project regarding the construction and the CO2 capture and utilization prototype in the cement industry. Also in our research group also develops CO2 membrane processes from some sustainable applications. In this presentation, we have divided into three different sections. First of all, I include some general concepts about the membrane technologies. Maybe if there are some people in the audience that are experts in this field, maybe there are some obvious concepts, but we prefer including these general concepts in order to establish some of the bases of this field. And later we will explain two of the different research lines that we develop in the research group regarding the CO2 capture. First of all, by using CO2 capture driven membrane processes, and secondly, using non-dispersive absorption processes by using hollow fiber membrane contactors with ionic liquids. So we will start with some general concepts about the gas separation technologies and membrane processes. Well, as you know, there are several technologies available from the gas separation, including, for example, the pressure swing absorption that later we will explain by our colleagues of SINTEF, the cryogenic distillation, absorption, and stripping. And among these different alternatives, the membrane technologies offers operational and economical some advantages, for example, low power consumption and costs, simplicity in the operation, compactness, portability, scalability, and continuous operation. However, there are some also drawbacks in this type of process. For example, the operating temperature that are very modest operating temperature, the limit gas purity, and a trade-off between the productivity and the selectivity of the membrane and the membrane processes. In this sense, the membrane technology is preferred from the modest product purity requirements and small-scale operations. What is a membrane? Well, a classical definition of the membrane is that it's a selective barrier that allows that certain particles, iron molecules, pass through blocking others. And the membranes are typically thin layers of material, natural or synthetic, that separate two phases, usually, for example, fluid phases, and control the movement of the substances between them based on size, charge, solubility, and other properties. The membranes, could be used in different applications. In this topic, we focus on the CO2 capture, but could be used in the gas separation, the water purification, chemical processes, on biomedical devices, among other types of applications. When we speak about the membrane, the more important concept is the flux. The flux is, the rate at which a substance passes through a membrane per unit of area. And in the membrane field, flux is usually expressed as the amount of material that moves through the membrane surface per unit of time and per unit of area. The flux is a critical parameter in the membrane processes because it indicates the efficiency of the separation or filtration processes. and the higher flux typically means, well, more efficient separation or a faster process, or it must be balanced with the membrane selectivity and the potential from the fouling of degradation over the time. Well, about the gas separations, membrane separation, there are typical separation, for example, the separation of the hydrogen and nitrogen, the separation of the hydrogen and carbon monoxide, carbon dioxide and methane. There are some typical gas membrane separation, and one of the most common characteristics of all of these industrial applications is the use of membrane based on polymeric materials, with some classic polymers being predominant. What is the general concept about the permeation mechanism? Well, the basic concept that gives the selection of the appropriate membrane material is for our application, and generally the gas transport in non-porous dense membranes occurs via the solution diffusion mechanism that involves three main steps. First of all, the sorption, the first step, the sorption of the gaseous penetrants at the upstream side of the membranes. Secondly, the diffusion of the penetrants across the membrane. And third, the desorption of the penetrants at the downstream side. When we speak about the membrane, there are two different figures of merit that is very important. The permeability of a given, in this case, polymer gas pair is determined by the product of the diffusion coefficient and the solubility coefficient. And secondly, the selectivity of the gases, which is defined as the ratio of the permeability of each gas, and therefore is given by the ratio of the diffusion and solubility coefficient. So when we speak about the membranes, it's very important to speak about the permeability and the selectivity, which is generally plotted in the Robinson's plot that, well, later we show a diagram, a typical diagram of the Robinson plot from the separation of the CO2. It's very important to design the membrane modules that involves considerably several critical factors to ensure the optimal performance, efficiency, and durability. And well, here in this slide, we can see some general design requirements for the membrane modules. For example, the thin active layer of the membrane, high permeability from species I and low permeability for species B, assuming that we only have, in this case, separating only the compound A from the compound B. Stable membranes with long service life, mechanical strength, very important, large surface area of the membrane in a small volume, easy to clean if in the case if necessary, inexpensive to build, low operation cost, among others. About the geometry of the membranes, the typical, we have 4 examples about the geometry of the membranes. We started with the plate and the frame modules, which is the most simplest configuration. In this case, the membranes are arranged as a flat sheets stacked between the spaces within a frame. And the most important advantage in this configuration is the simple design, easy to manufacture, high packaging density, easy to clean, maintain. That's the most simplest configuration in the membrane field. The challenges of this configuration: the lower surface area to volume ratio compared to the geometries, and the higher pressure drop due to the flow distribution complexities. About the second configuration, or the most typical second configuration, maybe is the spiral wound system. In this case, the membranes are wrapped around a central tube in a spiral configuration with feed spaces and permeate channels. And here, the most important advantage in comparison with the plate and frame modules is the high surface area to volume ratio, which is one of the most important parameters that we have to follow in this application. And about the tubular membranes, well, we have a typical tubular membrane, and the most important, or maybe the most promising configuration, is the hollow fiber membrane. That is the second figure. In this case, well, this consists of a bundle of thin, flexible tube-like fibers with high packaging density. And the most important advantage in this configuration is, well, the extremely high surface area to the volume ratio, the low energy consumption due to the small pressure drops, the compact and suitable from high volume separation, and well, it also has some challenges in this configuration that are, well, prone to the fouling and fiber breakage, and are more difficult to clean in comparison with, for example, with the last configuration that we saw it in the last slide. Negatively impact long-term performance. Well, all these types of configuration, well, has some advantages, but also important challenges. And I think that one of the most important parameters in the membranes is that it's a very flexible technology. So, well, here in this slide, we have some about the flow patterns. Well, it's very important to take into account the the completely mixing system. You can operate it in a piston flow system, different flow of the flies. But I think that it's very important to remark that it's a very flexible configuration. We can operate it with different parallel membrane contactors in series, parallel and series, in order to increase the productivity or the effectiveness of the separation. We can operate in different types of configuration, in permeate in series, countercurrent. As you can see in the figure, we can operate it with different configuration of membrane. That is one of the most, from my point of view, one of the most important advantages of this type of configuration and technologies. And well, once we can see a general concepts about the membranes, we present one of our research lines that we are carrying out currently the research group, that is the CO2 capture by pressure-driven membrane processes. And in this sense, it's very important to remark that among the different types of material that are available in the market, from the CO2 capture, the polymeric membranes have become an interesting popular technology from the CO2 capture due to their advantages and capabilities. And well, in this slide, we have some of the advantages that we have from the CO2 capture by using polymeric membranes. For example, the effective separation, because they are very high selectivity from the CO2. The lightweight and flexible technology, cost effectiveness in comparison with other materials, scalability, and in this sense, among the different types of polymeric commercial membranes that are available in the market, as you can see in the table, for example, there are available in the market some prism membranes, Polaris membrane, that is one of the most typical membranes from the CO2 capture, PremSaled, polyactive, sonary membranes. In this sense, in the research group, we are focused at this moment in the polysulfone and in the silicon membranes because, well, there are some advantages. For example, the polysulfone are very low cost, high mechanical strength, good thermal and chemical stability. And the silicon, well, there's a greater CO2 permeability, also flexibility and stability and resistance to the fouling. So these materials has very interesting applications. And as you can see in the table, it also has a very interesting trade-offs between the permeance of the CO2 and the selectivity of the CO2 and nitrogen. About the geometry, well, as we can see in the last slides, and we can comment it, well, the hollow fiber membrane contactor is one of the most promising geometries because the most important advantage is the higher effective area per module compared to the flat membranes. So we can have a very high area in a very small volume. Well, about the experimental system that we use from the CO2 capture, well, it's a very easy experimental system. We have the feed gas that we can use synthetic gases or real gases from the industry, our membrane. So in this sense, we have two different types of membrane contactors. As we can see in the last table, we select the iron manufacture which is composed of polysulfone with the hollow fiber membrane contactors. And similar with the PremSaled, which is composed of silicon, PDMS material. We can see the specific area and the number of fibers of these different membrane contactors. And well, experimental setup will be developed operating at higher pressures. This is the characteristic of this type of experimental setup. And we measure how to assess the behavior of our process. We measure the CO2 flow rate and the CO2 concentration in the output streams of the membrane in both the permeate and in the retenate streams, As we can see in the slides at the beginning, the most important typical figures of merit in this field is the permeance. That is the measure of how easily a specific component passes through a membrane, typically normalized by the membrane thickness and expresses the flow rate per unit pressure difference. And the selectivity, which is the ability of a membrane to separate one component from a mixture, typically expressed as the ratio of permeabilities between the two components. So when we speak about the membranes, we have to speak about the permeance or the permeability and the selectivity of a compounds in comparison with a mixture. Here we have some results as a way of example. For example, the permeability of the CO2 and the selectivity of the CO2 and nitrogen, and similar with the CO2 and oxygen, and operating, for example, with a difference of pressure of 4 bars and with a specific flow rate of 650 milliliters per minute. We can compare here in this table the result that we obtain of permeance of the CO2 and selectivities with different types of membranes, with different types of samples, synthetic gases, real gases from the different industries here in Spain. And we can see that, well, the membranes operated in a good performance in terms of the permeance of the CO2 and the selectivity of the CO2 and nitrogen, but we can see that the separation of the selectivity of the CO2 and the oxygen is very difficult. We can see that the selectivity is very close to 1, so it means that the separation of these compounds are very difficult, and that these membranes currently doesn't operate in a good performance because, well, we operated with streams that has different, we have CO2, nitrogen, and oxygen as the main compounds, so the separation of the CO2 and the oxygen are very difficult. But in this Robinson plot, in which this is the most typical figure that we can see in the membranes, in we plotted, in this case, the selectivity of the CO2 and the nitrogen and the permeance of the CO2, we compare here our results, but we compare the results that we obtaining from this application with other polysulfone membranes that are plotted in the green color, also with the PDMS membranes, and comparing with the upper bound Robinson, we can see that, well, for this application, there is a very a trade-off between the selectivity of the CO2 and nitrogen and the permeance of the CO2. So maybe some membranes has a very high permeance of the CO2, but the selectivity of the CO2 and nitrogen is lower. And from the other hand, maybe we can have a high selectivity of the CO2 and nitrogen, but the permeance of the CO2 is low. We can make similar with the selectivity of the CO2 and oxygen, but there is no available any Robinson plot at this moment in the literature from the selectivity of the CO2 and oxygen. So I think that one of the most important challenges in this line, in this research line from the CO2 capture by using membrane-driven processes is, well, finding a material that has a very high selectivity from the CO2, but a permeance of the CO2, but at the same time can separate in an effective way the CO2 from the nitrogen and the CO2 from the oxygen, and if we have other compounds, other types of compounds. And now we started with the last part of the presentation, in which we focus with the other research line that we developed in the research group, which is the CO2 capture by non-dispersive absorption processes. This process is, well, as you have already known, the chemical absorption based on amines, particularly the monoethanolamine, is currently considered the most viable technique from the CO2 absorption using the post-combustion technology. In this type of absorption, the gas enters to the bottom of the column, while the amine solution flows in from the top in current to the gas at atmospheric pressure. In general, the absorption operates at low temperature, and once the solution has absorbed the CO2, this liquid streams to the top of a second column that is known as the desorption column of stripper processes. This stripper of desorption processes operates at high temperature, normally very approximately to 400 Kelvin. At this temperature, the absorbed carbon dioxide is released from the top of the column, while the regenerated solvent is recirculated back to the absorption column. However, this process has some disadvantages, that are, well, the high energy consumption, large size of the equipment, solvent losses due to the evaporation, and for this reason, we developed an alternative, which is the non-dispersion absorption processes. This process proposes enhancing the conventional method, and we focus on 2 points. First of all, we replace the conventional equipment from hollow fiber membrane contactors, and the second point is change the monoethanolamine, the typical absorbent, with ionic liquids to avoid the solvent losses. In this case, the membrane contactors offer several advantages, including a large contact surface area per unit volume, operational flexibility, control of the gas and the liquid flows, that is one of the most critical parameters in this process, high energy efficiency, the modular design, and not solvent losses. Well, also we have some drawbacks, for example, the membrane resistance, the vulnerability to the chemical attack, fouling, but these issues can be solved by selecting suitable materials from the fibers and absorbents and adjusting properly the flows of both liquid and gas rates. From the other hand, well, as we can see now, the ionic liquids, we have a lot of ionic liquids that is, well, the ionic liquid have gained significant attention as a potential absorbent from the CO2 capture because we have some advantages, for example, the negligible vapor of pressure, high chemical and thermal stability, tunable ionic liquids, selectivity of a specific compounds, and well, that the ionic liquids also can be regenerated. However, well, some of the drawbacks of these ionic liquids is, well, the corrosion, the toxicity, the high cost. Well, we have also we have to develop also some ionic liquid that maybe can be effective from the CO2 capture. The experimental system that we use from the CO2 capture, well, we employ a commercial polypropylene membrane contactor that was also employed in both absorption and desorption stages. And as an absorbent, well, this recent line has been developed in a very high detail in the last years in the research group. For example, two types of ionic liquid that we employ. This is a physical ionic liquid. It is the amine ethyl sulfate ionic liquid. That the most important advantage is the low cost and no toxicity. And the second ionic liquid is the amine acetate, which is a chemical ionic liquid. And well, the most important advantage is the high CO2 solubility, the no toxicity, and well, this is the most important advantages of this type of ionic liquids. About the experimental system, also where we employ, in this case, we employ a feed gas mixture of carbon dioxide of 15% with nitrogen in order to work in a typical range of a typical coal-fired power plant that is more in this range of value of CO2 concentration. So this technology, we don't operate with this technology currently with real gases of the industry. And well, the experimental system is very easy. Well, the gas mixture was introduced through the cell side of the absorption module in a counter current and nearly atmospheric pressure. The ionic liquid was recirculated in a closed loop from a tank and through the fibers of the modules at a constant flow rate. It's very important here to fix the flow rates of both liquid and gas flow rate in order to maintain the pressure gradient outside and inside of the fibers. And finally, we measure the CO2 permeate from the rich solution to the cell side through the gas-filled membrane pouch. And finally, well, the CO2 was enriched at the vacuum pump output. So what is more or less the performance of this CO2 capture system by using non-dispersant absorption processes. And well, some of the results, but well, we have in this research line a lot of results. So if you are interested, we can comment in more detail. But well, in this slide, for example, we plotted some of the absorption results that we obtained with different materials of our membrane contactors, PP, PS, and PDBF with different types of ionic liquids. But in general, well, it's very important to remark that, for example, as we can see in this figure, as the temperature increases, the efficiency also increases when using, for example, the amine acetate with the polypropylene membrane contactor, obtaining efficiency very close to the 40%. And well, in contrast, for example, when we're working with the ionic liquid amine ethyl sulfate, the efficiency is not affected by the temperature. It depends, for example, as a function of the type of ionic liquid, different phenomena are involved. For example, if it's a physical ionic liquid, chemical ionic liquid, so different phenomena are involved in this process, and this is important to remark in this figure. The efficiency has been calculated as the ratio of the outgoing CO2 to the incoming CO2. And to finish, well, we have some results that we're obtaining with the desorption results. With the desorption results. In this sense, well, we can obtain in the desorption results an efficiency of 91% with the amine acetate ionic liquid. And we compare here with other types of ionic liquid that we tested in the research group. But well, it's important to remark this desorption efficiency is the amount of CO2 that is recovery in comparison with the CO2 that is introducing in this process. Well, one of the most important challenges in this technology is the desorption state. in this sense, well, as we commented at the beginning, one of the most important disadvantages of the conventional CO2 capture technologies is the desorption stage because, well, the energy consumption are very high. But in this sense, in this stage of processes, well, the desorption step is also a challenge because one of the research lines that we develop is make the desorption by using a pressure bank regeneration. And well, we have to operate it with a very low pressures, and well, we have to optimize this process in order that, well, increase the effectiveness of the process and bring it to a future implementation at an industrial scale. From my side, that's all. Well, I would like to thank again SINTEF for organizing this workshop, and well, if you have any question, I am available here to answer you. Thank you very much.
Thank you, Guillermo, for this super nice and complete presentation. Does anybody have any questions? Yes, we have a... Yeah, go ahead, Thomas.
Yeah, thank you. Guillermo, can you tell me something about the CAPEX, OPEX, and energy demand per kilogram of liquefied carbon dioxide?
At this moment, I can tell you about the energy consumption. I know that we developed previously in the research group. We compare the energy consumption of these non-dispersive absorption processes from the CO2 capture. We compare with the conventional technologies. I know that it's not my work, also the work that we develop in the research group, but I will share with you, if you're interested, some manuscript in which we have published this information. I don't have currently this information on my head.
And you have also no energy demand per kilogram of carbon dioxide because you need to give it a slow pressure and then you heat it up to recover it?
I know that the estimation that we develop, this energy consumption are not very high in comparison with the conventional technologies. Because it's true that we have to work with a very low pressures, but in comparison with the conventional technologies that we have to work, for example, with temperature very high, is not very. So the comparison of energy consumption are not very high. I will share with you, if you're interested, the results, because we have in some of the manuscript that we have published previously. Okay.
Okay, thank you.
Welcome.
Any other question? I have a simple one regarding the durability. There was a slide that you put, it was in the range of years of the typical polymeric membranes.
The durability of the membranes, well, all of the membranes that we presented are commercial membranes, so the durability are very high. So are membranes that are the duration of the time have a very high duration. But for example, one of the disadvantages of this technology is that, well, the fibers have very nice duration, but for example, the external shell is made of plastic, for example, and in this case, maybe we can detect sometimes some problems, not with the fibers, but also with when we take the shell, when we, for example, we introduce the ionic liquid. I think at the end the shell is not very flexible. Well, the material is plastic, so we have some problems with this.
But it's more the structure, not the membrane itself.
Yes, the structure of the membrane contactor rather than the fibers, because the fibers, well, I think that maybe after 1 year of operation, lost some of the durability and the performance of the process. But in general, the problem is this, for example, we can detect it with the polypropylene membrane contactors from the non-dispersive absorption processes. Because from the other application, we work at very high pressure. For example, with a difference of pressure between 5-6 bars. So these membrane contactors are more compact.
Okay, thank you. Yeah, so they need some eco design, the membrane itself.
Yes.
Yeah.
Yes.
Yeah. Thank you very much.
Welcome, Monique.
Okay, so if we don't have any more questions, so we're not so far away from the planning, I can invite Lucas to talk about the liquid solvents for CO2 capture.
Yes, let me just share my screen.
Not yet.
Not yet. No. But maybe could you stop sharing your screen?
Sorry.
Yeah. Oh. Good. So can you see the screen now and hear me clearly?
Yes.
Okay, good. Thank you. Yeah, my presentation will be about the absorption side of the CO2 capture. Guillermo gave a short introduction to the absorption process already, so I won't go into detail, but just stress some of the most important parts. But just first a little bit about me and my background. So I'm involved in the CAPTUS project through SINTEF. I work at SINTEF, and I'm active in the work package 5 for optimization of the CSAR CO2 capture pilot, and also in work package 2. And my background is a little bit that I did my PhD at the Norwegian University of Science and Technology, and there I worked with absorption-based CO2 capture, specifically modeling the degradation of amine solvents. So this is also something I will focus on a little bit later in the presentation. So first, as I said, I will just give a brief introduction of what absorption-based CO2 capture is and how it works, some of the advantages, disadvantages. And then we'll focus a little bit more on this post-combustion capture with amine solvents. And then I would like to give you a little bit of an overview of the status of the technology, how it's being applied in industry, what type of pilot studies are running, and what some of the operational challenges are with these operations. And finally, I would just like to highlight some of the process control strategies that focus on managing the solvent and making sure that the process is efficient and reliable. So absorption-based acid gas removal, there's a couple of technologies. First, of course, there's the physical absorbents. These are typically applied for applications where there's either high pressures or high CO2 contents or high CO2 partial pressures. And you can think here of purification of syngas or natural gas processing. And maybe you've heard of some of these solvents like Selexol and Rectisol. And then on the other side, there's these chemical absorption solvents. And this mainly consists of aqueous amine solvents. And I've given 2 reactions on the side to see how these solvents interact with the CO2. So in the first reaction, you can see that the CO2 dissolves into the amine and it forms a carbonate, and this carbonate is stored. And in the second reaction, the carbonate is the CO2 is dissolved into the solvent, and the carbonate that is formed reacts with the amine to form a carbamate. And these are the 2 ways that the CO2 is stored in the solvent. And by forming this chemical bond with the amine, the capacity of the solvent is increased significantly. So this is also why these type of solvents are typically used when there's lower pressures, lower CO2 partial pressures. For example, during post-combustion capture, where the pressure of the flue gas is typically around atmospheric pressure. So these types of amine solvents and their processes are, they have widespread use in the refining and the chemical industry. And what really marks these processes is the high maturity level and the scale of implementation that we see. Now, there's also the ionic liquids and nanofluid, and Guillermo also touched upon those, so I won't go into detail on those here. But I will mainly focus on these aqueous amine solvents. So on the right here, there's an overview of what the typical capture process looks like. The flue gas enters into the absorber and rises through the column. The solvent, the lean solvent, is entered at the top of the column and flows down. And in this absorber, the CO2 is selectively removed from the process, from the flue gas. And the solvent is then pumped through the heat exchanger and is heated in the stripper. And at these higher temperatures, the CO2 desorbs and is collected at the top, where the regenerated solvent is collected in the stripper and is recycled to the absorber. Was there a question or? No? Okay, and I'll just continue. An advantage of the process is that it's very versatile and adaptable. There's no need to integrate the capture plant into existing infrastructure, and it's most often just retrofitted into an existing process. The flue gas composition can vary, and the process can easily be tuned to accommodate for that. Also, as Guillermo already mentioned, maybe the largest disadvantage of this process is the high thermal energy requirements. And those lie typically around 3.5 to 4 gigajoules per ton of CO2 captured. And that's for the base case using MEA as a solvent. There's been a lot of development into alternative solvents that show lower thermal energy requirements. But they bring other challenges to the process. Some of these I will go into detail more later as well in this presentation. Yeah, so the solvents are key for the technology, and their characteristics can really make or break the process. So some of the key solvent considerations are their fundamental chemical properties. You can think of reaction kinetics, the CO2 capacity, so how much CO2 can be stored. In addition, the physical properties are very important. Viscosity, volatility, and foaming. The viscosity can affect the mass transfer rates in the absorber and desorber. Volatility of the amine can lead to emissions, and foaming can really disrupt the performance also of the process. Also important is the resistance to degradation, so the stability of the solvent in the environment and the corrosivity of the solvent. Then also the toxicity and the environmental impact. So what are the effects on the health or possible exposure, and what happens if the solvent is released into the environment, possibly through emissions. And then finally, also always important is of course the cost of the solvent. The operational cost, so the makeup cost of the solvent of the process. So I've shown here a couple of commonly used and studied solvents. So monoethanolamine is I would say the old, well-known benchmark. It's given here. MDEA is a popular amine. And apart from just single amines, you will also see blends of solvents that try to combine some of the positive functional properties of each of these individual solvents. And here a very well-known mixture is the open Caesar-1 solvent, which is a mixture of AMP and piperazine. In addition to these solvents, there's also proprietary solvents, such as the CanSolv, the KS1, or the DMX1. Of course, we don't have the exact composition of these solvents. But it's very likely they're also amine-based solvents, probably with some additives to enhance performance or to inhibit corrosion or degradation, etc. So I'd just like to give you now an overview of one of the applications. Maybe some of you are familiar with it. It's the Petranova carbon capture facility in Texas. You can see on the image on the right, the big tower, the big square tower here, that's the absorber column. So this is where the CO2 is removed from the flue gas. And the smaller, I say smaller, it's still a pretty big column, but the smaller column to the right here, that is the stripper column, where the CO2 is removed from the solvent again. So this plant is located at the lignite-fired power plant, and it captures around 14,000 kilotons of CO2 per year, where it removes 90% of the CO2 from the flue gas. In this process, they use a proprietary solvent, which is the KS1 solvent by Mitsubishi. The project has been operated since 2017. Operation was suspended in 2020, but it's been resumed in the autumn last year. And this installation really demonstrated the technical feasibility of post-combustion capture using absorption. But there were a lot of operational challenges, especially in the first couple of years. Now, in the report on the operation, it was mentioned that some of these operational challenges were to be expected for such a first of a kind project at a large scale, where there's a lot of integration between different parts. But yeah, it's definitely something that has to be considered. And I can imagine also for other technologies that are not at this scale yet, these problems will probably be encountered at some point. What caused these plants to suspend operation was the lower than expected oil prices. So the CO2 that was captured was used for enhanced oil recovery. But yeah, due to the low oil prices, the economics didn't work out. Yeah, some takeaways from this project is really to try and come up with a robust and reliable design, and also to make sure that there's plenty of supportive political and economic conditions, because those were important for this project. So if you look now more in general at these absorption-based capture plants, we see that technologically they are feasible, but there's a reluctance to commit from different companies or governments. And I've listed some of the main reasons for that here. So first, of course, is low profitability. So CO2 as a product, it's not as valuable as oil or other chemicals. So you can see that these type of projects really depend on subsidies or carbon taxation. There's a high uncertainty. We have a carbon credit price that is fluctuating, political support that is also fluctuating quite a lot. And it's also important to take public opinion into account. There's a challenge of establishing a value chain. So there's a lot of significant initial investment required to make sure that the CO2 that one captures is also transported and then used or stored in a location. To get this initial infrastructure in place, a lot of money and a lot of technology is required. And then finally, there's still quite a high technical risk. So there's only been a few large-scale projects, and there's limited operational experience overall. So investing in this type of technology is very high risk. So to address some of these operational challenges and the uncertainty in this technology, there's a couple of steps one can take. First, of course, is to get a good overview of the general performance of different solvents and their energy use. Also, it's important to get an overview of the solvent degradation and deactivation, and monitoring how this changes during the duration of the capture campaign. It's important also to monitor corrosion of equipment, and seeing how that affects dissolved metals in the solvent and also the if the material and the equipment will remain. And then finally, an important topic is emissions. And here it's not necessarily the CO2 emissions in the flue gas, but mostly amine emissions, so solvent emissions, and some of the degradation products that can be emitted. So in the last part of this presentation, I would just like to cover some of these topics to see what some of the steps are people use to mitigate some of these challenges, and to see how a properly managed CO2 capture facility could look like. So degradation of amine solvents, you can see the process on the right here again. There's two main types of degradation. There's oxidative degradation, which mainly occurs in the absorber, where the CO2, the flue gas containing the CO2 often also contains oxygen, and this oxygen reacts with the solvent. And then there's thermal degradation, which occurs mainly in the parts of the plant with increased temperature. So in the bottom of the stripper and in the reboiler. And this solvent degradation causes loss of amine, so functional loss of the capture solvent, but it also leads to the production of degradation products. And these can have various effects on the process. So first, of course, a loss of amine will lead to reduced capacity and a reduced performance. But the presence of degradation products, on the other hand, they can change the properties of the solvent. So it can increase the viscosity and it can lead to more foaming, indirectly, therefore, affecting the performance. In addition, some of these degradation products, they can be volatile. You can think of ammonia for most of the amine solvents. And this will lead to an increase of emissions and might need mitigation to meet standard requirements. So some of these degradation products also have shown to increase the corrosivity of the solvent, so they can lead to corrosion of equipment. And in some cases, solvent treatment is necessary to remove some of these degradation products and to reactivate the amine. And this solvent treatment comes at a cost. It's also important to note that, of course, corrosion is important to monitor for the integrity of the equipment, but there's an additional effect at play here. So the metals can dissolve into the degraded solvent, and some of these metals, like iron and copper, that are typically found in the construction materials, they're found to catalyze the degradation and to speed up the degradation of the solvent. So here in the plot on the right, I've shown typical trends in an MEA capture process. So this is from a post-combustion capture plant at the Heilbronn, and this is the first year of the testing program. So you can see that they've analyzed the solvent for the duration of the campaign, and they've analyzed it for formate and oxalate, which are typical oxidative degradation products, sulfate and nitrate, which are typically impurities in the flue gas, and then iron, chromium, and nickel, which are metals that have been leached from the equipment. And this type of behavior that you see in the plot is seen in a lot of different pilots and different processes. So it's really common behavior. And what you see is that there's stable initial operation. So the solvent is quite a good condition. And then after around 800 or 900 hours, then suddenly there's a deflection point where the concentration of these degradation products and the metals start to increase. So what we expect that is happening here is that the formation of degradation products leads to more corrosion and an increase of iron in the solvent. And this iron then catalyzes the degradation rates, leading to more degradation and more products. And you could call this a degradation runaway. And this is not a sustainable operation. So this will spiral out of control quite quickly. And at some point you would have to replace the solvent or treat it to remove the impurities and get back to this stable operation. So there's a couple of ways that this solvent degradation is managed. Some plants use symptomatic treatments, such as corrosion inhibitors or anti-foaming agents. And although these resolve some of the issues temporarily, they don't fix the underlying problem. So they don't, they're not a permanent solution. You can think of modifying also the process to prevent degradation. For example, by selecting a solvent that is resilient towards degradation, or by removing certain flue gas impurities. You can change the process conditions, for example, lowering the temperature in the stripper, or reducing residence times. For example, reducing the residence time at which the solvent is in contact with oxygen can also reduce degradation. And there's also been some research of removal of dissolved oxygen from the rich amine stream, for example, through nitrogen sparging or using membranes that can selectively remove oxygen before it can react. Apart from that, there's also active solvent treatment known as reclaiming. And the three main technologies here are thermal reclaiming, and there's ion exchange and electrodialysis. And I've given the example of thermal reclaiming here on the right. So a small side stream is taken from the reboiler and is entered into the reclaimer. Here the solution is brought in contact with a strong base to release some of the impurities and to free up the amine. And then the amine is boiled off and returned back to the stripper, to the process flow, whereas the impurities and the degradation products remain behind in the reclaimer, and they're removed as a waste product. I have to note that ion exchange and electrodialysis, these techniques, I won't go into detail here, but these only remove charged compounds from the solution. So if you have degradation products that are that don't have a charge, then these technologies won't be able to remove those. So now we've had the solvent degradation. I'd also like to spend some time just on the emissions, process emissions. And this is an issue when some of the solvent or degradation products, when they are entrained in the cleaned flue gas, so the flue gas exiting the absorber. And this can be volatile emissions or aerosol-based emissions. And what we typically see is that most of these emissions are aerosol-based, meaning that there are small droplets in the gas in which degradation products or amines are dissolved, and they enter with the gas stream. So as I told you, typically you will find amine solvents that are emitted, volatile degradation products like ammonia, but also harmful degradation products. You can think of aldehydes, formaldehyde, acetaldehyde, or nitrosamines if they are formed in the process. There's a couple of mitigation methods that can reduce emissions, and they are applied quite frequently in capture plants. So firstly, there's the preventative strategies again. So we can remove impurities from the gas inlet, or we can try to inhibit the formation of aerosols, or try to inhibit the growth of aerosols. Then there's a range of demisters that can be applied to remove aerosols. And we typically also see water washes being implemented, and in some more rarer cases, acid washes. And in the figure on the right here, there is an example of a water wash. So you can see the purple inlet here. This is the top of the absorber where the solvent is entered. And in addition to the structured packing below, there's an additional section of packing where water is circulated. And so the gas is brought into contact with this water, and so
you are muted.
Yeah. You're muted. Now.
Now it's better?
Yeah, yeah.
I was not muted the whole time, I hope, right?
No.
No,
No,
not at
okay.
all. No, not at all. No, no.
We would
no.
have said it. Don't worry.
No,
Okay,
don't
thank
worry
you.
at all.
Yeah. Okay. Yeah, another mitigation method is, of course, effective solvent management and continuously monitoring the gas phase and the solvent. Final example I want to show is a pilot plant at RWE at Niederhausen. And this pilot plant is known for really having long-term campaigns and investigating what happens with the solvent over time. You can see here how they implemented these different strategies. So you can see that they have a dry bed and a water wash to prevent emissions. They have pre-treatment and pre-scrubbers. And they also tried this ion exchange solvent reclaiming. And in some of the results that they published, you can see that the use of, for example, the ion exchange here really impacts the concentration of impurities in the solvent, and that the use of this reclamation can be quite effective at controlling the quality of the solvent. So for the solvent management, we know that there's technical solutions available to limit the degradation and emissions, but they come at an increased cost and increased complexity of the process. It's also important to note that waste handling and disposal of these degradation products and impurities can be quite costly. For example, for thermal reclaiming, you would produce a hazardous waste, which is quite costly to handle and dispose of. So I think the real question here, and this is something maybe research should focus on, is finding effective solvent management strategies. So finding the right degree of reclamation or emission mitigation, where the process can be kept at good operating conditions without spending too much cost on managing reclaiming and emissions. So to conclude, you could say some people say that the CCS deployment has consistently fallen short of expectations. And I think a main reason for that was that there's really a reluctance to commit to large-scale post-combustion capture pilots and plants. So there's as I said, a financial uncertainty, but there's also limited operational experience. So I think how to accelerate this deployment is to really get effective legislation and long-term support from government instances, and also to foster collaboration and growth of CCUS hubs and building these CO2 value trains. From the process understanding, there's a couple of things that should be investigated. There should be focus on really understanding degradation and corrosion mechanisms, and be able to predict. It's impossible to identify and monitor degradation products and emissions over time of the processes. And there should be focus on implementing effective emission control and good solvent management systems. So with that, I'd like to conclude. If someone has any questions, feel free to ask, or feel free to contact me at a later point as well.
Thank you very much, Lucas. It was very insightful. I like as well that you really highlight the non-technical barriers, right? I think this is a big issue for this kind of topic. In the end, you need a lot of energy. I was wondering, because in the end you have the regeneration, so you heat up the solvent to, let's say, release the CO2. What is the temperature that is typically applied?
Yeah, so the temperature depends on of course which type of solvent you use and the pressure at which you operate. So if you operate at a higher pressure in the stripper, the process gets more efficient, but the temperature increases. For typical MEA solvent process, you would see a temperature of 120 degrees, I would say.
Okay.
And this is really limited by the degradation. So you can go to higher temperatures, but then you risk having a lot of thermal degradation there.
Yeah. So really understanding these patterns, right? Or finding different solvents. I think there is a lot of room for exploration here. Because if we think about the temperature to regenerate, plus if you want to recover, right? If you identify indeed this contamination runway and then you want to distill back the solvent, then there's a lot of energy that is needed. So I imagine that this is indeed big shortcoming for this technology.
Yeah.
Any other question from the audience? So if not, I think the next we had a short break. So we can, I don't know if you agree, being 5 minutes, very short, just so we don't miss the agenda. So we can be back in 5, and then it's gonna be Henri talking about solid sorbents. See you very soon.
Okay. See you soon.
Okay, so we can move to Jan Hendrik, no? How do I pronounce?
It's Jan Hendrik, or
Oh.
I also go by Henri.
Henri.
So that's also okay.
Okay. So I was not missing so much. Good.
Yeah, that was very close. Yeah, so I assume my audio works fine. There has been a Windows 11 upgrade forced on us recently, and I had some issues with my headset earlier this morning, but yeah, so I'm good if it works fine.
Yes, we can see the screen, so feel free to move.
Okay, hi everyone. So as we already established, I'm Henri, or Jan-Henrik Cloete. So for those of you that have not met me at the previous consortium meetings, I'm a researcher here at SINTEF based in Norway. So my background is chemical engineering, but then also reactive multi-phase flow modeling. But then in recent years, doing a lot of work in general on developing new reactor concepts. So in that regard, our group has done quite a lot of work on carbon capture. Not with the solvent-based processes like most people in Norway, I would say. So mostly on solid particle-based processes. And part of this work has been on post-combustion adsorption-based capture. So I have quite a bit of background in that, but I have to admit it's on quite specific focused processes. But today I'll try to just give you a very broad overview of adsorption-based capture, the different technologies and options there, and also the advantages and limitations of different approaches, to just give you an overview of what is possible with the technology, but also where the limitations are. I also feel like I should add a disclaimer. Unfortunately, this week fell into an extremely busy week for me with 2 EU consortium meetings and a bunch of reporting deadlines. So I had a bit less time to prepare for this than I would have liked, but I hope you can still get something interesting out of this presentation. Okay, so to just give a short overview of what I'll be discussing, I'll start with a short introduction, what adsorption-based CO2 capture are, and also a broad overview of the general advantages and shortcomings of it. And then I'll look into 3 different categories that can be used to divide different adsorption-based technologies. So the first is the solvent that is used. The second is what method is used to regenerate this solvent, so release the CO2 from the solvent, and then what reactor type you use. And then to try and put this a bit into practical context, I'll go into a bit more details on the 2 specific technologies that we're developing in our group at SINTEF, called SARC and CESAR. And since CESAR is also will be used in the CAPTUS project, that hopefully will also give you a bit more understanding about what the technology is that we're actually using in CAPTUS. And then finally, I'll just end up with some summarizing thoughts about my opinion of where adsorption-based CO2 capture stands. Okay, so starting with the definition of adsorption-based CO2 capture, that is a process where CO2 is selectively adsorbed to the surface of a solid solvent, and then this CO2 can be desorbed again in a concentrated stream by changing the operating conditions. So overall, there's two different types of adsorption. So one is physisorption, which is the adsorption that's based due intermolecular or van der Waals forces. That is between the CO2 models and the molecules and adsorbent surface. And in this process, the adsorbate or the surface are left in contact, so there's no chemical changes in the two parts taking place. And so, as a broad overview, these physisorb processes are usually better for higher CO2 partial pressures. So the other category is chemisorption, where the bonding involves a chemical reaction that creates a new chemical bond between the surface and the CO2 molecule. And the kind of broad classification of chemisorption is that usually these are more sensitive to temperature swings. So the adsorption is more dependent on what the temperature is. But this also means that you have higher desorption entropy, so you require more energy to release the CO2 than for physisorption. But on the other hand, in general, the chemisorption processes, since it's a stronger bond, has a better selectivity to adsorbing CO2. So as I mentioned, so you can release the CO2 again in a concentrated way by changing the operating conditions. And this can basically be done by two ways. So one is heating up the solvent. So since the desorption reaction is endothermic, if you make the temperature higher, that shifts the equilibrium to releasing the CO2 again. And then the other option is to expose the solvent to a lower CO2 partial pressure. So these are called pressure swing processes. So trying to make some very general overviews of what adsorption processes are good to compared to the commercial solvent-based processes that Lucas discussed in detail. I should say that these are some very broad classifications. It depends extremely on what process you're looking at. But in general, we can say that there's lower energy demand for the capture using solid solvents. So this is partly because of lower regeneration entropy, but also that in solvent-based processes, there's quite a lot of heat demand to recover water that is evaporated in the process. So that's something that you avoid in adsorption-based processes. But as Lucas has mentioned, there's also quite a lot of development on solvent-based processes that can reduce this energy demand as well, bring the two closer to each other. In general, also, the reactions are much faster for solvent-based processes. So this is partly because of the intrinsic kinetics that are faster, but also partly because you're using solid particles, you have a very high gas to solid surface contact area, which is more difficult to achieve with liquid gas flows. So you get a larger surface area for the reaction and less mass transfer limitations. And then mostly the adsorption-based processes also avoid some of these challenges that Lucas discussed in terms of solvent emissions and degradation products. But some of the disadvantages of solvent-based capture, so in general, this is at a substantially lower TRL than the solvent-based processes, and there are fewer commercial alternatives available in terms of solvents, which limits a bit the scale-up of the processes using the solvents as well. Another challenge is that it is more difficult to move and distribute your solid solvents than it is with a liquid that you can just pump. So that has some implications for what kind of reactors and what kind of processes you can use. And then lastly, if you want to do indirect heat transfer, it's also more challenging because the thermal conductivity in the packed bed of particles is quite a lot lower than it is for a liquid in a solvent-based process, for example. Okay, so then Looking into the sorbent, so here's quite a long list of the different things that you want in your ideal solvent. So I'll just go very quickly through this, not very comprehensively, but this is mainly just to show that there's quite a lot of things to keep in mind, and probably you will never have the perfect solvent that will be able to do all of this exactly the way you want. There's always some compromises. So the first thing that you want is high adsorption capacity, but perhaps a bit more specifically, you want your adsorption capacity to change sharply with changes in your temperature and pressure, so that you can very easily exploit a difference in the loading on your solvent. And this allows you to reduce the amount of solvent that you need in the process to capture a certain amount of CO2, limiting the operational cost, and also in some cases allows you to make your reactor smaller. Secondly, also very important is that you want a high selectivity for your CO2 to adsorb to your surface. So this is, for example, a challenge with physisorption, that in some of the solvents, there's also a tendency, for example, nitrogen to adsorb to your surface. And then when you regenerate the solvent again, then you regenerate your nitrogen as well, and then you reduce your purity of your CO2 stream. So then perhaps you need another process after that to further purify your CO2. It's also very important to have a high tolerance to moisture. So in all flue gases, there's some degree of moisture. So in some cases, it can be quite high. So then it's in quite a few solvents, there's the challenge that your CO2 and your water can competitively adsorb to your surface. So if all of your surface sites are occupied by water molecules, you can't adsorb CO2 as well. So to avoid that, then you have to do drying of your flue gas before your capturing process, which adds some additional cost. Another important factor is to have a high tolerance to flue gas impurities. So there's things like SOx and NOx and other impurities in flue gas that can chemically degrade your solvent and reduce its working capacity. You want fast reaction kinetics to reduce the reactor size. You want a low regeneration entropy to reduce the energy that you need to release your CO2. You want to be able to use mild regeneration conditions, so that allows practical operating conditions and less costs. You want your solvent to be mechanically unstable over long lifetimes, so that you don't have to replace your solvent and adding to your cost. And then obviously you want your solvent to be cheap, otherwise that can add substantial cost to your process. So here's quite a nice table that I found in a review paper that's cited here. So I think if anybody wants a quick overview of adsorption-based CO2 capture, this is quite a nice paper. I won't go into the details here, but I just quickly want to give an overview of the different types of solvents out there and some of the key features or benefits of the different ones. So one category is activated carbons, which are the main advantage is there's a lot of source materials for that, and they're low cost and widely available. But the downside is that they can have limited CO2 capture capacities and low selectivity to CO2. A way to overcome this with carbon materials is to use more synthetic carbon nanomaterials that through well-defined pore size distribution a specific surface can increase the adsorption capacity, but then the manufacturing of these adsorbents are a lot more complex and more expensive. Then there's also a lot of work on using natural zeolites for CO2 capture. So for those not from a material background like me, so zeolites are a group of microporous crystalline alumina silicate materials. So they also, since they're naturally occurring, there's a large availability and a low cost. But since these are natural materials, their purity is low, and that can lead to limited separation performances. So then there's also work on synthetic zeolites that can then increase the adsorption capacity and have a more pure material, but then again, your solvent becomes more expensive. Then there's also a lot of work on metal organic frameworks or MOFs, which again, for people not from materials background, are porous polymers consisting of metal cluster that's linked with organic ligands, so which can give you very nice structures that lead to very high surface areas, and you can tune the properties of your adsorption process basically with it. So this allows you to get very high CO2 adsorption capacities, but these materials are also a lot more expensive to produce. And the last group that I have here is amine functionalized materials that are using similar amines as in the solvent-based processes. So the advantage is there's a lot of supports that you can use for this active material that you put on it, and compared to some of the other things I mentioned here, the cost is reasonable for these kind of materials. But then similar to the liquid solvents, then if you have some potential challenges with degradation at high temperatures and in the presence of oxygen. Okay, so next I'll go into the regeneration types. So first are pressure swing processes, which relies on a variation of the pressure, or specifically partial pressure of CO2 to regenerate the sorbent. So one option is to do PSA process, where you have the adsorption at high pressure, but you desorb at atmospheric pressure. So this is a well-established commercial process. For example, I think in demonstration 1, PSA process is used, but I think there it's actually used to separate CO, and you only get left with a CO2 concentrated stream in the end. But using this for CO2 capture, one of the disadvantages is that you also have to for post-combustion, you have to also compress all of the nitrogen that's in your flue gas, which adds quite a lot to the compression cost. And also the selectivity to CO2 tends to drop at higher pressures. So in general, it seems like for CO2 capture, alternatively vacuum swing adsorption is usually preferred. So most of the research is going into here. So where you have your flue gas at atmospheric pressure, so you do your capture at atmospheric pressure, but then you desorb on a vacuum. So the challenge with this is the cost and operational challenges with drawing very deep vacuums can be quite high and challenging. So quite often you need multiple stages of vacuum swing to be able to get high purity and high recovery of your CO2. So just some general observations on PSA processes. So here on the right is an example of a cycle that can be used for vacuum swing adsorption. So first, we can just ignore the second and the fifth boxes here. So just look at the 4 stages here. So what you basically do is you keep the pressure at atmospheric, you feed your flue gas, and you adsorb your CO2, and you mostly have nitrogen coming out. Then you next have an evacuation step where you draw a vacuum, and you basically pull off most of your nitrogen and reduce the pressure, but you stop before you start getting your CO2 out of your reactor. Then in the first step, you switch the direction and you draw a deeper vacuum, and then you get out your CO2, which you can then have as a relatively pure stream. And then in the end, you use your nitrogen to repressurize your reactor again so that you can go back to the first step. So this is kind of the simplest way to do this. But then to be able to get higher purities and recovery rates of your CO2, then it's quite common to use a 6-stage process where you add these stages where you use some of your nitrogen coming out to push out the CO2 in this step, and then use the CO2 to fill up the reactor with CO2 before you start drawing the vacuum. So that's a way to get a higher purity from this process, but obviously add some further complexity. So in general, vacuum swing or pressure swing processes are better for higher CO2 concentration. So this is very dependent on the process and what concentration you are, but that can be a general statement. And in general, also physisorbents are used for these processes, which tends to have a lower regeneration enthalpy and a lower temperature sensitivity. So then you don't worry about the heat being released in the capture and the heat required for the regeneration. So as I mentioned, these are based on well-established commercial processes, which makes them easier to scale up and commercialize, and they use very simple packed bed reactors. And one other interesting thing is, since you just need to compress or draw vacuums, all you need is electrical energy inputs, which makes it easier to retrofit into existing processes, and since you don't need this large amount of thermal energy to be able to regenerate the solvent. Okay, so next up we have temperature swing processes, which relies on heating a solvent to release the CO2. And so this heating can be done in two ways. So the first option is to use direct heating, where you basically feed the hot gas directly into this bed of particles. So the main advantage of this is that you can have very high heating rates because you have a very large surface area for your particles and you contact directly with the gas. But then the challenge is what gas to use. So the obvious choice is steam, because you can easily separate out the steam afterwards by condensing the water. That also helps by giving a partial pressure swing for your CO2. So by reducing the partial pressure of CO2, you shift the equilibrium to releasing more CO2 as well. But the challenges are that you firstly require a solvent that's not sensitive to steam, as I mentioned with this challenge. But then probably the biggest issue is that since you have to condense all of your steam again at the end, you can't really recover that energy from the condensation entropy at a usable temperature. So you have to add a lot of steam to be able to do a certain amount of heating, which makes the process quite energy inefficient. So the alternative is to use indirect heating, where you basically have a heat exchanger inside your reactor, for example, tubes with a liquid flowing through it. So the advantage is you don't have these issues related to purging gas. It allows you to recover the condensation entropy of your steam or other working fluid that you're using. But the challenge is that you have lower heat transfer rates because the heat has to be conducted from this tube into the particle bed, and especially for packed bed, this thermal conductivity can be reasonably low. And then if you have low heat transfer rates, then you also need a lot of this heat transfer surfaces, which can add quite a lot of cost to your reactor. So just some general considerations here for the temperature swing processes. So on the right is just a very simple example of a three-stage temperature swing process. So in the first, you feed your flue gas with CO2, you adsorb, you also release a bit of heat during this process, but then you adsorb most of your CO2 in the process here. In the second stage, you heat up your reactor, and that allows you to release your CO2 again at a higher temperature. And then before you can cycle back again, you have to cool down your reactor again to get a low temperature where the adsorption reaction is thermodynamically favored. So in general, temperature swing processes are more suitable for lower CO2 fractions, so especially below 10% of CO2, I would say, because you don't have this constraint about for pressure swing having to draw extremely deep vacuums that becomes costly. An advantage is that heat is usually cheaper to get than electricity, but then you also need more of the heat. So there's a bit of a trade-off there. So alternate or different to the pressure swing processes, since you need this heat, it can be difficult to retrofit existing processes since you need some kind of heat source. Otherwise, you have to build a new boiler to generate heat. But then if you have waste heat available at a suitable temperature, that can be quite a good approach to do. If you have to do large temperature swings, you can have issues related to solvent degradation. And then also if you need higher temperature swings, you need your heat at a higher temperature where there might not be waste heat available at a high enough temperature to do that. And then, as I mentioned, the solvent thermal conductivity becomes more important for packed bed configurations. Then lastly, I'll just quickly mention, so you can also do hybrid processes that combines the temperature and the pressure swing. So the main advantage is of this, since you combine it, you can regenerate at milder temperatures of both your temperature and your pressure, which can reduce the issues that you have with both temperature swing and pressure swing processes. But the trade-off is then you need equipment for both pressure swing and temperature swing, which can increase the complexity of the process and also add some additional costs. Okay, so then, yeah, I'll have to speed up a bit, but so just quickly looking at the different reactor types. So there's essentially three that's commonly used. The one is to use a packed bed reactor, where, as in the finger here, you just have a bed of particles stacked on top of each other, and the gas flows between the particles. And an important characteristic is the plug flow behavior that you have in this reactor. So you would, over time, have this front of your CO2 concentration moving through the reactor. But so the advantage of this is that you can time it in a way that you basically stop the process just before your CO2 starts breaking through the reactor, and you can get quite high capture efficiencies with this kind of process. It also uses quite simple packed beds, so it's relatively simple to operate and scale up. But some of the disadvantages are that since you just do a batch-wise process in a single reactor, you need a cluster of these reactors that work in a coordinated way. You can have quite high pressure drops in these kind of systems because your reaction is actually only happening in the small part of the reactor where the front is. So you need quite long beds with substantial pressure drops. I mentioned the poor heat transfer in packed beds before. And then there's a challenge related that since your reaction only happens in this front, you get quite a lot of heat being generated there, which then shifts the equilibrium away from capturing your CO2. So there's some challenges with dealing with that as well. And to reduce the pressure drops, you usually have to use larger particles, which then introduces some mass transfer limitations and reduces your reaction kinetics. Okay, so the next option is to use a moving bed reactor. So they basically have particles falling downward under gravity, and you have countercurrent flow of gas moving upward. So compared to packed beds, the main advantage is that you can have continuous operation possible. You can have high capture efficiency because, so for example, this is a laboratory system that's in a different group at SINTEF where they built such a process. But so you can see for the adsorption section, your gas is being fed at the bottom. And then as you move upwards, your CO2 concentration will reduce as the CO2 gets absorbed. But at the top, you feed completely fresh regenerated sorbent. So your very lean CO2 flue gas is in contact with highly regenerated CO2, which allows you to capture that last bit of CO2. So this allows you to get very high capture efficiency. And then you, for various reasons, also get lower pressure drops than compared to a packed bed process. But there's some challenges with circulating these particles in these systems and also distributing them over a large reactor. There can be quite large mechanical stresses on the particles that leads to degradation of your sorbent. You can't really implement pressure swings because your different sections have to be linked for the sorbents to flow there, so you can't really change the pressures between the different sections. And you have relatively low heat transfer coefficients, but higher than packed beds. Okay, and then the last part that I have, and that's what we've mostly been working on, are fluidized bed reactors. So in fluidized bed reactors, gas is introduced into a finer bed of particles, and then introducing a fluid-like kind of behavior. So some of the advantages for this is because you use smaller particles, you have faster reaction rates than for packed beds. You also have very good mixing in these reactors because of the fluid-like behavior, leading to higher heat transfer rates. Since you have good mixing, you're using basically all of the solvent inside the reactor and not just this front. So you can have smaller reactors as well. And since the sorbent almost behaves like fluent, it's easier to transport between reactors and distribute over a reactor. But the disadvantages are is that while you have advantages to the good mixing, as I mentioned, you actually want this kind of more axial segregation plug flow kind of behavior, which you then don't get in a fluidized bed. So you need, as in this example, some segregation between your sections of your reaction so that you can get some more axial segregation in your CO2 loading on your solvent. I unfortunately don't think I'll go into the details of showing this this nice animation here. And then also another challenge is just mechanical attrition of your particles, because you have this very chaotic system of the particles moving around. Then I have a section on some examples from the work that we've done that kind of integrates a lot of these concepts. I unfortunately see I'm out of time, so I'll skip over this section, but you can find the slides online for me, more details, or we can have a chat at the next consortium meeting, and I can explain some of the concepts for you in person. So I'll just wrap up with some kind of summarizing thoughts from our side about the absorption-based processes. So something that I've seen quite a lot is that there's a lot of focus on developing solvents with very high working capacities, which is nice, but what is more important is how much of that working capacity you can use and at what cost. So that brings me to the next point. So these solvent-based processes are quite a complex optimization process where you have to consider your interaction between the properties of your solvent, your reactor, and your process. And so for that, we've been doing quite a lot of work in our group to use some standardized modeling methodologies to be able to optimize and compare different processes, and also for specific solvents. And then you also typically have quite a lot of competing performance criteria in these systems. So then it's quite good to combine them all into levelized cost of the capture to be able to get a single objective function basically for optimizing the processes. So another thing that I can just briefly mention, so here very much focused on post-combustion capture, but something that is also very relevant, specifically for this project, I would say, is direct air capture, because for fuels where you typically combust the fuel at the end of the life cycle and release the CO2 again, so processes like we use in CAPTUS can avoid other CO2 capture or CO2 emissions, but to really get the carbon neutral fuel, you even need to get your CO2 from bio-related processes or from direct air capture. And adsorbents, for several reasons, seems to be the thing that most companies are going for direct air capture. So there's quite a lot of potential in that area as well. And then just lastly to conclude, so there's definitely quite a lot of promise in adsorption-based CO2 capture. It has potential to substantially reduce the cost of the CO2 capture compared to solvent-based systems. But unfortunately, in general, development has been too slow, and there's at this stage where there's suddenly CO2 prices in Europe where a lot of these processes would be economically feasible. It's a problem that these processes aren't commercially available, and the maturity is nowhere near to the solvent-based processes. So it's a matter of if these technologies would be developed rapidly enough to be available for the market when we really need to capture a lot of CO2 in the coming years. So therefore, the conclusion is we definitely need a lot more research in this area and more knowledge and more operational experiences. Okay, thank you very much. Sorry for going a bit over the time.
Thank you so much. This was super interesting. I have a very quick question. I don't know if anybody else, I see no hands. Feel free to, has to be quick though. For this direct air CO2 capture in the air, wouldn't it be a problem to use the sorbents because of the very low CO2 concentration, if I understood well?
I'm not an expert on this, but from what I understand, these temperature swings and especially the chemisorption sorbents, they are relatively better at capturing these low fractions, but it's
Okay.
always the low fractions are always a challenge. It will always be a lot more expensive to capture
Yeah.
from atmospheric concentrations than in industrial concentrations, but
Yeah.
the solvents are relatively better at doing that.
Okay. Thank you. Yeah, I totally agree with you. A lot to be discovered. There is really a need to push research and industrial pilots. So good that we are doing that with CAPTUS. So yeah, I think we're good on time. Perfect on time actually. So I would like to thank all the speakers again. It was really insightful, and we have recorded the session. Also in the chat, there is the link to the presentations. And yeah, you can always reach out to the speakers or check the slides for more information.